It's actually been a few months since I did my first video. A bunch of stuff kept me from working on it, but during that time I discovered an interesting hidden feature of that 68HC11D0 chip. But first I need to rewire some things. Since port C is destined to become the data bus, I have to find other pins to blink. Port A seems obvious, but it has two missing pins in the DIP version, and only a few of the pins can be set to output mode. Port B will become the high address bus. My best option was to use port D2 through D5, which are used for the SPI interface. I also added a dip switch for the two mode inputs. I only had a 3-position switch handy when I filmed that, but I had a 2-position switch on order and put it in. And here's what its schematic looks like now. We have the CPU chip, the clock generator, the reset switch, some pull-up resistors, the mode switches, and the serial port is on D0 and D1. There's also the LEDs on port D and port C. And now, the hidden feature. You see, the 68HC11D series is designed to have 4K of ROM in it, but the D0 was sold as not having a ROM. That actually means is that you're expected to configure its inputs so that you can ignore any ROM that might be inside. It's cheaper for a semiconductor company to reuse the same masks for different versions of the same chip. In other words, it's cheaper to build it with a ROM, any ROM, and then have the customer ignore the ROM. It's even possible that all 68HC11D series chips use EEPROM memory, even the factory programmed ones, so that they wouldn't need to make special masks for custom ROMs. So if there's an unexpected ROM, what's on it? I've heard stories that sometimes it could contain someone else's code from a canceled production run, but the main thing I had heard was that it had Buffalo on it. What's Buffalo? That's the monitor program you saw in the first video running on the evaluation board, but it's 8K and this 68HC11 only has 4K. To find out, I set the mode inputs to start in single chip mode instead of the bootstrap mode. I also set the serial port to 9600 baud, which is the standard speed for Buffalo. Surprise, it came up right away. Hey, this is neat. I need to dump it right away. Then I can disassemble it and compare it with the full version. And I did. Guess what? This Buffalo thing uses most of the 192 bytes of RAM just for its own purposes. There's an 8-byte chunk of RAM that isn't used by the 4K Buffalo, but otherwise it's as much a 0-page pig as the full version. Fortunately, there's still a whole 48-byte chunk, which is enough space for an LED flasher. A small LED flash program fits into the RAM reserved for a bunch of unused interrupt vectors. Now it's started up. That's funny. Why did it stop? Maybe it's a bug after the first time through. I'll just make it go faster. Now it runs more loops, but still stops. What's up? What has happened is the watchdog timer, aka COP or computer operating properly, has tripped. In single chip mode, this is turned on at reset. There is a way to turn it off, but the catch is you can only write the register once per reset. Then it becomes read-only. This is the no cop bit in the config register. Change the config register at 3F from 02 to 06. Then start the LED flasher again. And it stays on. And you see I forgot to turn it back on. You have to do it every time you reset. And now it stays on. But that's not all. Another of those registers that you can only write once, HPRIO here, changes the chip mode. You can manually change it into external bus mode. And that's where my next challenge awaits. I can add an external RAM or ROM, start up in Buffalo, and manually change the bus mode. Then I can explore the external address space to confirm that it's working, and finally set it to start up in expanded bus mode. But that's for next time. See ya!